Great, so in this example, number 25, we're going to find that there are occasions where you in fact have complex eigenvalues, which you would expect since they're the roots of these polynomials, and so we get those complex roots sometimes. And when that occurs, we're not going to worry too much about determining the eigen vector for those, but we just want to recognize it. Now, in this case, though, notice we're going to have, since it's a 3 by 3 matrix, we're looking for 3 eigenvalues, counting duplicities. And since I've already told you there's going to be some complex numbers, you should be able to figure out, well, complex numbers always come in twos when you're finding the roots of a real polynomial. So there will be at least one real root in this one as well. And so that's just from my hint and the knowledge of algebra. So recall the way we solve this is we want to subtract off lambda from the diagonal and then take a determinant of this. So this could be more or less disgusting depending on which row or column you choose. So I'm going to go ahead and actually choose this last column there with the signs plus minus plus. So the first one would be 1 minus lambda, excuse me. So it's going to be 1 times the determinant of -1, 3 minus lambda, -4 and 13, 0, and then we have plus, so -1, I'm going to write this actually with a parentheses, -1 minus lambda inside the parentheses, and that will be multiplied by the determinant of -1 minus lambda, 0, -1, and 3 minus lambda. Okay, there's my determinant there. So we'll finish writing this out and say this first one gives me -13 minus 12 plus 4 lambda. And this last one gives me -1 minus lambda times -1 minus lambda times 3 minus lambda. Great, so we would actually want to multiply this out so we can insert these things in the formula with it. So let's do that as well here. The only thing I need to be careful of when I took this first determinant right here, I forgot to subtract off -4 minus these things. So this actually turns out to be a plus and a minus. So kudos to you if you caught that before. Now we're going to change colors a little bit here just to make this work. So this is turns out to be 1 plus 2 lambda plus lambda squared. The other way of factoring out -1 from each and then doing 1 plus lambda. Now we multiply by 3 minus lambda. And these things over here, just -1 minus 4 lambda. Who is the best animal at the farm? It's the lamb. Duh. Alright, so I'm just going to multiply the 3 through it here. So 3 plus 6 lambda plus 3 lambda squared. And then subtract off the lambda, so minus lambda minus 2 lambda squared. Let me scooch over a little bit here. Minus lambda cubed. And I don't really need this parentheses actually. So this is -1 minus 4 lambda. Alright, great. Now let's put everything together and say this gives me a negative lambda cubed. Let's group all our lambda squared. So I have this one and this one. So we have plus lambda squared. Let's group all our lambdas. So I have 3 of them. So that'd be 6 minus 4. So that'd be a single one. So plus lambda. And then our constants, I really have here just -1 plus 3. So plus 2 is equal to 0. Alright, great. So now we need to factor this. So in order to do so, I would notice there's not a whole lot of options for me, right? So I don't see factoring by grouping because I don't really see a good pattern here. But what I do know is that if there's any real numbers that solve this, or at least that are rational, the rational numbers would be some factor of 2 divided by some factor of -1. So that makes you think they're either going to be plus or minus 1, plus or minus 2. If there is a rational root in this, it's going to be one of those ones. So you could check pretty fast. If I check 1, I'd have -1 plus 4. So that's not going to get me 0. If I check -1, I'd have, let's see, -1 here, give me +1, 1, -1, 2. So those don't work. But what if we plugged in a 2? So if I plugged in a 2, I'm going to do that with synthetic division, because when I plug in the 2 with synthetic division, it will actually also, if it does give me the root, factor it for me. So if I plug in the 2 here, the way to do it with synthetic division is just bring the first one down, multiply that by 2, place it here, add straight down, multiply that by 2, place it here, add straight down, multiply that by 2, place it here, add straight down. Good, so I got a 0. So that tells me that 2, in fact, is a root. And this right here tells me the coefficients of the rest of it. So this would relate to lambda minus 2, since 2 is a root. Then we'd have -1 times lambda squared minus lambda minus 1. And you know what? If you're not happy with that, you can stick the negative way out in front and make these all positives. That might make it a little bit easier on the next step. So this is equal to 0. So now I'm able to solve this by just plugging in this into my quadratic formula. Right. So to find my other ones, I'm going to do lambda, let's say 2 and 3, since this one I'm only going to make lambda 1, will be -b plus or minus the square root of b squared minus 4 all over 2a, or just 2. So I'm going to write it like this. Or -1/2 plus or minus I root 3/2. Great, so let's go ahead and find some eigenvectors. So I'm going to start with the nice and easy one, where lambda 1 is just equal to the value 2. So plugging this into our matrix, so recall, we're going to take the original matrix and subtract 2 from every element on the diagonal. That will give us the matrix -3, 0, 1, -1, 1, 0, -4, 13, and -1. So I want to find some vector that when I multiply this, it'll give me 0. So again, I could go for reduced row echelon form if I chose. But this one, it's good enough to just find some vector that works. And so what I'm going to notice is take advantage of is these top 2 rows, each has an x component and just one other one. So if I were to consider some vector where the first component is 1, I could determine what the other components would need to be in order to make the multiplication by each row 0. So if I did the first component 1 and last component 3, that would give me 0 when I multiply that top row. And then likewise, if I did the first component 1 and the middle component 1, that would give me 0 when I multiply the second row. And that's what's really nice. So x, for that first component, is sort of a party friend who hangs out with z sometimes, hangs out with y sometimes. Very, very gregarious fellow. So here's my vector. And it has a vector space of dimension, or an eigenspace, excuse me, of dimension 1, since there's only one vector that corresponds to this eigenvalue. Now, likewise, with the complex roots, it does get a little bit more, shall we say, interesting, because when you plug in, let's say we plugged in lambda 2, which we'll call the -1/2, take the plus 1 first, plus I root 3 over 2. So using that one, if I plug that into my matrix, I end up with a matrix that looks like this. I'm going to do it in yellow for no actual reason. So -1 minus this stuff would be -1/2 minus I root 3 over 2, 0, 1. I would have then -1. So 3 minus this would be 3.5, so 3.5, which is also 7/halves, minus I root 3 over 2. the last element is 0. This is kind of hard to see in the top one. 0, 1. And then the last row has stuff in it. I'm just going to look at these two. So notice this in this top one here, and this middle one, there are some interesting factors. So what we're going to think about here is, well, what would I have to choose from my different divides to make things work? So because the top one has just the two elements, the x and the z, and the middle one has the x and the y, we could do a little trick in order to find out what this vector has to be. And one way we can go about this is looking at that middle row. Let's start there. We really have an element that's -1, this more complicated element. Then we have a 0. And so what I could recognize is those are the first two components. So for my vector, so I'm thinking if I multiply this by a vector, what will give me 0? I would really just switch the order of those two components, here and here, and then change the sign. So let's switch the order. So we have, maybe I should give myself a little bit more room. So 7/2 -I√3/2. So the -1, but we're going to change the sign of one of them. So I'm going to make this positive 1. So these are my first two values. So then I could either, I didn't write everything on the third row. I could use that, but I could also just use the information from the first row here and say, well, why don't I just consider what would happen if x is multiplied by these values here, and see what I get for my z value. So what we would do there, I'm just looking for a little bit more space since I'm at the bottom of my screen here. I'll just sort of scooch over a little bit to the side and then we'll come back. We'll do it in green. So this vector, I'm looking for like what the heck does z have to be if this is my x. So if I take that and multiply by the top row, I would have so -1/2. So this is from the top row of the matrix. That's a 2 down there, times the element in my vector, minus I√3/2. And then that would be plus z needs to be equal to 0. Great, so in order to solve this then, we're just going to FOIL it out. And this would give us -7/4. Then we would have the outside, so it would be plus I√3/4. The inside would be minus I7√3/4, excuse me, plus I² 3/4. Recognizing, of course, that I² turns into -1. So then when I put this all together, so I² -1, so that would be -7 minus 3/4, that would be -10/4, minus a 6√3 over 4, so that's plus z. Plus z is equal to 0. So z would have to be, the version of this. So this actually does simplify the -5/2 minus 3√3/2. That should have an I with it. Sorry. Plus z is equal to 0. So z would be the negative version of this. Let's just go ahead and stick that in. So z would be 5/2 plus I3 √3 divided by 2. So there's the eigenvector, and likewise you would do the same thing for the other eigenvalue. And what's pretty great about the other eigenvalue, so if I were to do the very similar thing, but I plugged in -1/2 minus I√3/2, then this is going to be almost identical, except you would just change to the complex conjugates. Change those signs. And then you'll be done. All right, great. And now I'm not going to worry too much about the spaces of them.